Thank you, Peter, for the introduction and for having me, and good afternoon to everybody who joined the session. So I'm very happy to be part of this important series of fire safety webinar, especially dedicated to the facade. So to start, a few words about Saint-Gobain. We design and manufacture building solutions to improve people's health, safety, and well-being. Saint-Gobain has been active in the construction market for more than 350 years, with a significant presence in the Middle East with many local production sites. We share ambitious goals and commitments to address global challenges, and we advocate for sustainable construction and for energy and resource preservation. Saint-Gobain is diversified into many businesses like gypsum, insulation, mortar, and glass, to name a few. In terms of fire safety, we have complete facade solution, as well as fire-resisting internal partition, glass, ceiling, pipes, and air ducts. So many combustible materials are used today worldwide in facade assemblies for many reasons, whether performance, application, aesthetic, or commercial. The most common ones include exterior installation finishing systems, so known as EIFS or ETICS, metal composite cladding, high-pressure laminate, and weather-resistive barriers. There has been a number of documented fire incidents involving combustible exterior walls, and a lot of studies have been done following that to better understand what specific scenarios are leading to these incidents and investigate current test method and develop potential mitigating strategies. So the topic I would like to address today is fire safety in facade, and more importantly, how the design and the choice of the appropriate materials can have a huge impact on facade fire safety. I will start with a definition and an overview of the reaction to fire test and standard, with a focus on the European fire classification. I will also be discussing the UAE fire code and the current limitation in terms of reaction to fire, but also fire propagation. I will give as well an overview of the European regulation and which fire performances and design measures they follow for maximum safety. And coming from the construction material side, I'll be giving some examples on materials, so with different classification, and I will focus as well on non-combustible material and why it's important to use them in facade. So, as Peter mentioned, we have learned so much from the past. I've put the pictures below to show that even without insulation, air cavity, or any finishing system on the facade, fire can propagate quickly. So through the weak points, which are the windows, as you can see on the first three pictures below, and the absence of balcony. So any insulation or finishing system that you put on the facade should not accelerate the fire propagation, but on the contrary, slow it down. So since windows are the weak points, they should always be studied with a proper fire safety design in order to avoid fire propagation from floor to floor. I will come back to this part with more details when we go through the European regulations. So what have we learned from unfortunate past event? I listed some of the key findings taken from a very good report. So you can find it on the Fire Protection Research Foundation report. The report shows that exterior wall fires are as dangerous as internal fires. Fire incidents happen frequently in country with no or poor regulatory control on combustible exterior wall, or where construction has not been complying with these regulatory control. Also, it's important to know that during a fire, people do not die because of the flame, but mainly because of smoke, so carbon monoxide and noxious fume coming from everything that is burning. Burning debris also can have a significant hazard and can cause downward fire propagation. Facade chimneys are dangerous and lead to more extensive flame spread, and also combustible exterior wall can present an increased fire hazard before finishing the facade, so before rendering. And this you can see it on the last picture on the right. So it's important to highlight that the combustibility of the assembly component directly impact the fire hazard. In addition to that, the reaction to fire regulation requirement have the most significant impact on actual fire performance and level of risk presented in the facade external walls. So What is reaction to fire? As you must all probably know, reaction to fire evaluates how a construction material reacts in case of fire and how it contributes to the fire expansion in the early stages of the fire, so before flashover. On the other hand, reaction to fire of an assembly is called fire propagation and is evaluated by large-scale fire tests. Because we cannot decouple both, I'll be talking about fire propagation as well so I'll be talking about fire reaction and fire propagation. And usually the best national fire codes, they combine the two approaches. So you have requirement for both. I'm not going to address fire resistance because it has been addressed in details in module 1. So reaction to fire test can assess several features of a construction material. First, combustibility, so whether a material is combustible or non-combustible. So if it brings no energy, for example, to a fire and it will not ignite or burn when subjected to fire, it's called non-combustible. Test to show how much energy and heat are released by burning the material. Ignitability and flammability, so the reaction to fire when in contact with the flame. We have also tests to determine the amount of smoke generated, flaming droplets, and also toxicity. In fact, I added it, although today there are no mandated tests for fume toxicity, but it's a topical subject and there are current discussion on the importance of including it. So as you all know, the UAE Fire and Life Safety Code addresses all types of exterior wall, both in terms of reaction to fire and fire propagation. It is considered as an advanced code because both testings are mandatory, even if you are using non-combustible material. I'm showing in the slide two types of systems, so the ethics or EIFS. So it's a complete insulation system with different layers, directly glued and anchored on the wall, and also ACP and MCM application, known as cladding, aluminium cladding panels. We started seeing in the market the approval of foams and some facade application, like for example, EIFS. So what I wanted to focus on today is some limitation of the code for combustible wall assemblies. So it's important to answer, for example, some questions like, is the code in its current state or version convenient for combustible assemblies? What can we learn, for example, from the European code and experiences, and what kind of improvement could be implemented to mitigate fire safety? So I will be addressing first the importance to categorize buildings as per their level of criticality, as we see for the ACP section, for example. Also, what is the best reaction to fire to consider? Is it ASTM or is it EN 13501? So what's the difference between both? And also I will have a list of the fire propagation test and to show which one is more appropriate for which type of application. So moving on to the first fire reaction, so ASTM E84, it's a US flammability test to evaluate the surface burning characteristic of a material. So it measures two parameters, the flame spread index and the smoke developed index. This test has been originally designed for internal walls, carpet, and ceiling, but then widely used in North America to characterize all types of construction material. So one of the limitations is that the sample is placed in ceiling position. So it cannot be easily correlated to performance in an exterior wall use. Also, this test does not properly assess thermodynamic thermoplastic material, which in fact tend to melt away from the assembly rather than spread flame in the horizontally prone test orientation. So there are three classes. Class A means that the material is non-flammable and not non-combustible, so big difference. Class A means that the flame must not propagate more than 25% of the whole tunnel, and smoke generation should be limited. So, for example, giving some example of material, PIR, phenolic foam, XPS usually easily pass this test. For EPS, it's more difficult. You need to have the right density and the right fire retardant to pass. And this is why sometimes EPS is tested as per UL 723, which is not exactly equivalent. And Christina is going to be explaining in detail why there is a big difference in the calculation or measurement when addressing thermoplastic material. So, what is the European classification of fire? So it's the EN 13501-1, which is the standard for evaluating all the characteristics of a construction material fire performances. So it applies a range of small-scale tests, and it is intended to classify these materials in terms of their contribution to fire development. And the standard was designed for controlling flammability of internal material, but also has been used for exterior wall system applied throughout most of Europe, applicable only to vertical walls and ceiling. So material can be classified into 7 different Euro classes according to the way that they react to fire. So from A1 to F. The product belongs to one of these 7 classes, but also you have to add additional classes which are related to the smoke development, and also so S1, S2, S3, depending on how much smoke they generate, and also the amount of burning droplets, D0, D1, and D2, depending on how much burning droplets they generate. So many tests are done to classify these material as per these classifications. So you have the first one, the EN ISO 1182, which is the non-combustibility test. There is also the ISO 1716, so you burn the product and you calculate the total heat generated. There is the single burning item, EN 13823, which determines the reaction of fire behavior exposed to the thermal attack by a single burning item. And last but not least, the ignitability test, so ISO 11925, which determines the ignitability of a product by directly exposing it to a propane gas flame. So based on these tests, the materials are classified. So I gave some examples here on the slide of insulation materials. So you can see mineral wool, which is stone wool and glass wool, compared to foams. So mineral wool are non-combustible materials, so they have the best classification, A1 and A2. And then the foams come for the rest of the classification because in nature they are organic, so they are combustible. So we have the class A, A1, which is the product A1 and A2, which are the products that are non-combustible. So they will not contribute to the fire growth nor to the fully developed fire. There is then the moderate combustibility, low combustibility material, so the Euro class B and C. For example, like phenolic foam, the surface is charring and doesn't melt, so slow propagation of fire. There is also the moderate combustibility material, Euro class D and E, which is EPS, XPS, PIR, etc. And last, the combustible material, so the Euro class F, which is material that don't pass any test or that hasn't been tested. So what are the limitations of the fire code when using ASTM E84? So this standard is only a flammability test, so it does not take into account more important reaction to fire parameters like combustibility and flaming droplets. Why flaming droplets are important? It's because some products can melt and ignite to form flaming droplets at another point. So it will create also a new fire and it will accelerate the fire propagation. So last but not least, in general, ASTM and UL are not suitable for thermoplastic, since during testing and once the fumes ignite, the energy causes the material to drip and melt on the floor, therefore cutting the flame's continuity. So moving on to the limitation in terms of fire reaction of the assembly or fire propagation, it's important to note that there are many large-scale fire test standards, as you have seen in Module 2. They all differ in many parameters, but most importantly, they have different level of difficulty. So here in this table, I listed them by order of difficulty. So the first one is the most stringent one, which is BS and ISO as well, because both are very close and give comparable results. So the strength of fire test is mainly related to the burning load, as you can see in the last column. For example, for the first two, it's around 450 kg of wood, more or less represent what you can find in most flats. So, for example, the furniture that you put in-house, indoor. Some of the tests use only 50 kg of wood, which is not realistic. So it's considered to be low and not stringent. There are ongoing discussion on this topic to try to define a harmonized European large-scale fire test with basically two options. So the option one would be for high-rise building or building receiving people. So here you would use BS or ISO. And the option 2 is for middle size residential building, less than 80 meter, for example, where you would use the German, for example, the NFPA 285 or the German test, which are less stringent. So in terms of fume toxicity, I wanted to address it as well, because most fire deaths arise from inhalation of toxic gas. So fire toxicity is an essential component of any fire risk assessment. Unfortunately, there is no recognized standard on fume toxicity. So Professor Hall, in a lot of his studies, you can also look into his work through articles that you find in the literature. So he has done some, in fact, some standardization. So he combined two standards, ISO 19700 and ISO 13344, which are used to define what we call the FED, so the fractional effective dose. So it's lethal power per gram of product. So as you can see in the graph, the fire toxicity of 6 insulation material was investigated under a range of fire conditions, and you can see the level of toxicity of each. You have glass wool, stone wool, phenolic foam, expanded polystyrene, PIR, PU, etc. So stone wool and glass wool showed consistently low yields of all the toxic products, whereas carbon monoxide, for example, is shown for the foams. It's produced whenever you have foams, so it creates toxicity in the fumes. As well, when you add to the EPS fire retardant, it's as well considered toxic when it burns. So now moving on to the fire regulation in Europe. So the table resumes here how it is generally assessed. So for high-rise and building receiving people, generally only non-combustible material are used with no large-scale tests required. In some other countries like France, you must pass a large-scale fire test like ISO or BS if it contains combustible material. For medium-rise building, there is a minimum Euro classification to use, and also you have a special design to limit fire propagation in the facade. So you have, for example, mineral wool bands, so stone wool bands around the windows, around the elevator and stairs, and also every 2-story, for example. So in terms of low-rise, usually there's no regulation for facade. And it's important to mention that for ventilated facade, you have to avoid any chimney effect. So you have to cut the air gap compulsory every 2-story. So it's present in approximately all the national regulation codes. So moving on to some examples. I wanted to give you some examples of fire tests with combustible material. So as you know, every insulating material has its own benefits and drawback. So it's very important to use each material in the appropriate application. So depending on the building criticality and the fire hazard. So here I show you first an example of EIFS system with phenolic foam and PIR. So they usually pass the large-scale fire test, no problem, because the foam char, so it doesn't melt. The only drawback is that it generates toxic fume, and you still have to put stone wool bands in order to limit the fire propagation towards all the facade. For EPS, it's much more difficult. It depends on the rendering system and as well on the stone wool bands, if you put stone wool or no above the window. It's important to note that even if the test passes, the large-scale fire test, you have all the EPS completely melted underneath the render. So, for European countries that have no or poor fire regulation, URMA, which is the European Insulation Manufacturer Association, created a document with the best recommendation to follow. Like, for example, in Spain or Italy, today you can install a 100% EPS ethics with organic render and no stone wool fire barriers on a high-rise building without any problem, so which is highly dangerous. So some countries also, like Austria, for example, they have no requirements to fire regulation except that the exterior wall should be non-combustible. However, in reality, combustible systems are applied as fire-engineered performance-based systems. So they passed as an alternative solution. So this is why URMA decided to work on a document with the best recommendation for each type of insulation. So for high-rise, for example, you have to use non-combustible material. For medium-rise, more possibility allowed if evaluated correctly, so through an appropriate large-scale fire test. So you can use several different combustible material as long as you have a proper testing or a proper facade design to limit the fire propagation. So the use of desktop studies to assess equivalence of product and system is not always properly managed or controlled. So the government should restrict desktop studies to only be used where appropriate. So when there is sufficient relevant, if you want, test evidence. So to that, I conclude on my presentation. I hope I didn't take a lot of time. So UAE has an advanced code today compared to other countries. Component and assembly testing are mandatory for all facade systems, including non-combustible. But there is some limitation. So for reaction to fire, for example, you have current reaction to fire requirements. They can be improved to better classify all material, including thermoplastic. EN, for example, 13501 should be very good in determining all the fire classification of all material. Also, it should include fire toxicity. In terms of fire propagation, since they have all different level of difficulty, it's important to create different categories of building and to also properly design the guidelines to limit the fire propagation. This is, of course, when using combustible material. And finally, with today code limitation and proper assessment of combustible material, the safest is to use non-combustible material whenever possible. So thank you very much. I will reply, of course, to all your questions at the end of the session.